ready. Let's go. All right. Well, thank you, everyone. My name's Sarah Jordan. I am the co-founder and CEO of Schooled LLC. I suppose I ought to give a warning in that there's a good chance that this talk's going to make some of you disagree, prompt some thought out there. A colleague of mine starts his talk saying, if I don't make at least half of you mad, then I've had a failure to communicate. But first, a little bit about myself. I am a metallurgical engineer with over 20 years in a range of processes, including casting, heat treating, and of course, machining. I also have been working in additive for going on about 7 years. About 13 years ago, I went over to what my husband calls the dark side, aka the business side of things. I have an MBA from Carnegie Mellon University, TIPE School of Business, one of the top business schools in the world and one of the top business analytics schools. After I graduated from there, I spent 4 years as the forecast manager for a $1.5 billion business unit at Emerson. I used to say that my job there was to make up numbers, and then I moved to a supply chain role where I made decisions with those numbers that I got from my successor who I had trained. So then I said my job was to make decisions with the made up numbers. Anyways, between those roles and working at 6 prior startups, including 2 I co-founded and 2 I partially own, I have a pretty extensive background in thinking about forecasts, business planning, and costing. We will get to the money side of things in a bit, but I want to talk briefly about forecasting. So first, anyone who uses forecasts should be aware that when predicting the future, that even when you're given a specific number, it really is a probability distribution. So if you think about basic statistics, if you're gambling and you get $1 for every time it comes up heads, we'll forecast that you'll win 50 cents on average, but really you have a 50% odds of winning $1 and 50% of winning 0. Forecasting is kind of like that. In that, a forecaster will give you some line out into the future, this gray line, but realistically, there's some probability distribution where, like if they gave you a range and say, okay, they're 50% confident that it'd be between these yellow lines, or they're 90% confident it would be between the blue lines. Actually, forecasters know that if you have to give a point number within a probability distribution, that actually the probability of that specific number occurring is close to 0, and that's why forecasts are almost always wrong. So which comes to my next point, some things to watch out for in forecasts and why you shouldn't blindly trust them, including the things I'm going to tell you later in this talk. First, there's always error. That's the difference from the prediction and accuracy. So, this should be something or is reported, but often isn't. Bias is the systemic difference between if somebody's constantly predicting high or constantly predicting low. There's often politics involved, and I don't mean by this the government, I mean interactions with people. So often there are things that are influencing the impartiality of the forecast, such as who's the forecast for, what your boss is telling you, what the PAC and general consensus is saying. All of these things can influence the forecast. Another thing that matters is what's the purpose of the forecast. So forecasts made by financial analysts on Wall Street have different purposes than if you're trying to predict the market for your own company or trying to justify purchasing equipment. Another key thing that is often not noted in forecasts in the media is what are they defining the market as? So thing I've noticed is that often in the 3D printing market, they'll group all kinds of things together, such as parts, service, materials, equipment, and it's not always clear what all they are including. Confirmation bias, that's you wanting to believe the forecast because it already fits in what you already think. And then finally, the thing to watch out for is the S-curve. Go into that a little bit more. So if you saw this curve, which looks pretty similar to the current history of additive manufacturing, where would you draw the line next? You might draw it like this red line, right? That makes sense. You're just extending it in the future. And if you're going to use time series modeling software, that's pretty much what the analytics are going to tell you as well. They're just going to be like, oh, extend that line. Well, the problem is, in this case, the left axis is actually market fraction, and it's the percent of the market who wants one, who has one. And actually, with market fraction, the maximum that you can have is actually 1. It goes asymptotically to 1. So the line's going to curve over at some point. At some point, everyone who wants a 3D printer will have one, or maybe they'll have more than one, but they'll have what they need. At some point, people who are going to adopt new parts, they will have done it. So at some point, this is what will happen to the growth curve. It's not going to go up linearly forever. Now, just so you don't think this is a theory, here's an example from an actual product that most of us are aware of, and many of us have on our pockets right now. And this is the Apple iPhone. So it went up fairly linearly for about 8 years, and then it actually dropped off before leveling off. At that point, people are just, for the most part, replacing an existing older model. Most of the people who would like an iPhone have one at this point. Now let's look at some forecasts for additive manufacturing. These forecasts are all pretty much going up, and it's pretty clear that no one is considering the S-curve phenomena yet, and that these things might taper off at some point. In fact, some people, like this pink line, are predicting exponential increases in the future. If you look at it, the year 2026, there's a really wide gap between the lowest and the highest, about between $20 and $70 billion, give or take, which is actually a pretty huge range if you're trying to make decisions with these predictions. Now, since I'm in metal 3D printing, I think, I wanted to look at what are the forecasts in that space, and they're pretty wildly different as well. This is for parts, not printers themselves, and there's predictions anywhere between $2 and $16 billion by the year 2028. Now, most of these people have pretty high compound annual growth rates, between 23, 30%. But you can also see that they have different starting points, because if their history is so far off, that they do have slightly different market definitions here. But they are wildly different. So, which brings me to my next point, and that when you're predicting the future, this may seem self-explanatory, but if you're assuming there's going to be some kind of technology developments, then you're going to get a wildly different result than if you're just assuming some kind of market adoption of the existing technology. Now, when we talk about additive manufacturing for parts, some of these are new to the world parts, but some of these are consolidating other existing parts or making designs that, could be made in other processes. So the question really is, what do we expect the ultimate available market to be for metal additive manufacturing? And to some extent, this is going to depend on how far the technology advances. Now, I saw a quote last year that said if metal additive manufacturing could achieve $5 a kilogram, then it would be a $100 billion market. Now, on one hand, that seems like an incredibly huge increase compared to the forecast that I just showed you. But on the other hand, it seems reasonable because that gets the price down below machining and in the neighborhood of formative processes such as stamping, casting, and other mass-produced parts. But that's a big if, getting down to $5 a kilogram, or for those of us in the US, $2.27 per pound. Now, for the prior 3D printing forecast, it's not clear. What are they assuming? What's the basis for their forecast going out 7, 8 years? Are they assuming an improvement in technology from the current state? Are they assuming big drops in costs from the materials and equipment point of view? And my guess is probably in a lot of cases. If they just expect metal AM to win market share, it's really not clear where they're expecting it to come from. But in some cases, they may just be extrapolating past growth trends into the future. So I want to try to go through some costs, analyze the costs of the current state, and analyze where we would need to go to get down to that $2 a pound goal. So this is some basic costing assumptions. It's going to be very basic math. Hopefully it's not too boring, but I'm going to go through this pretty quickly with a generic part. So if we look at powder bed fusion, and these are my assumptions, and you might disagree with them, and that's okay. You can redo this analysis and make different assumptions with your own numbers if you want. But I'm going to assume aluminum, and what are we going to start with as a reasonable powder cost? Now, obviously, powder costs can really vary depending on your assumptions, but I've picked $40 a pound, which right there we have an issue if the total cost of the part is desired to be around $2 a pound. Now, if we look at labor, if we assume $15 an hour and reasonable 50% is going to various benefits and taxes, that gives you an employee cost of $22.50 an hour. Now, these machines print relatively slow, about, let's assume, a cubic inch per hour. And based on the density of aluminum, we can calculate that you're going to need 10 hours to get a 1 pound part. So we know these machines are automated, and the person doesn't necessarily have to stand there the whole time. But I make the assumption that for this 10 hours that you're going to need 30 minutes of labor, or 11.25. Similar analysis can be done with, how much is the time for the machine going to cost? So, machine prices can be all over the place, but if we assume $100,000 and we divide this by 10 years for straight line depreciation, and we're running this 24/7, you can get a cost to operate a machine per hour. In this case, 114, and if it's again 10 hours to print a pound, then right there the equipment cost is going to be $11.40. Now, for comparison with some of the mass production rates, this is less of an issue. For instance, I got an aluminum melt furnace quote recently, which is $90,000. But the difference is that equipment makes 1 ton an hour of material. So doing the same analysis, it actually gets you a cost of 5 cents for the machine for 100 pounds of material. So it's pretty negligible in that case. But for 3D printing, the depreciation of the machines is a big deal. Next, we have post-processing. So those can be all over the place. But if I assume that we're going to ignore heat treating and basically just looking at support removal, the machining that's needed, I, in this case, just decided to assume 10% was a reasonable amount for machining. We get down so that the total, just adding up these basic costs, that the material cost is, about $70 or above 30 times our target goal here. So if I do the same kind of analysis with binder jetting, again, it has raw material costs. Now, in this case, they're a little bit cheaper, and binder jetting does have a somewhat higher production rate, so it's going to take less labor to go into this. It produces more pounds per hour. That part of it is actually directionally correct in getting the labor and the raw material costs down. However, we run into a different issue in that binder jetting tends to have much more expensive equipment. There's multiple pieces of equipment needed, such as for sintering as well. And I'm told that these typically run about $1 million. So if we're going to do the same kind of straight line depreciation for 10 years, that actually gets us to $11.42 an hour, or $4.45 per pound. I know that thinking about things on a per pound basis is not the most common thing, but if you depreciate faster, you'd actually have this per pound cost go up. But on the other hand, maybe you can ramp up your production rates to make it go down somewhat. But still, you're already well above this target. Now, post-processing in metal binder jetting is a little bit less because they don't typically require support material unless they're trying to deal with any kind of sagging during sintering. And it is a fairly accurate process, but I'm going to assume in this case 4% cost for post-processing. So 1757 is my rosy scenario assumption here, and it's still a fairly long way for the target, but it is better. Next, people might have asked me about sand printing, because casting is considerably cheaper. So in that case, if you just are going to look at the ingot metal costs, yeah, that is cheaper, $1.25. The problem is that when you print for sand, you actually have to print a good bit bigger part than the space you want. So if you want a part that's very simple rectangular prism, 1 by 2 by 5, you actually have to print a mold that's substantially bigger. And that actually means you have to print, in this example, 260 cubic inches of sand. So even at a very cheap 7 cents per pound, which I believe includes the labor and equipment and margin in there, that actually gets you $18.20. So right there, again, it's gotten way beyond what the target is. I need to add in this analysis some labor for the foundry itself, as well as the other issue with sand printing is tolerance control. So coming from a foundry background, sand casting actually has pretty poor tolerances. The molds tend to erode. Silica sand undergoes a phase change at high temperatures, which causes them to have tolerances that vary about 3%. So most sand castings get a lot of machining. One example, foundry part I looked at recently started at 5 pounds, and they actually remove 1.5 or about 30% of the weight. And that gives 2 problems. So basically, first, there's the machining cost itself. And then second, you're throwing away metal, which means you have a certain set cost, and you're actually dividing it by less weight for the final finished part. So in this case, I assume 20% post-processing costs. So again, the total cost in this analysis, $24.34 a pound, or about 10 times above the target. So if we're trying to get down to below $2 a pound, so far, are you depressed yet? I actually consider some of these to be kind of rosy assumptions, and we're still an order of magnitude away, and this is just for costs. So something to point out, costs are what you pay for something, but price is what you sell something for. And customers, they're looking at your price, considering it their cost. So none of this includes a whole host of other costs of being in business, let alone profit. So how do we get out the cost from this? Is this $2 a pound goal even possible? So some approaches to lowering costs fall in one or more of the following categories. So there is a bit of a problem here. Some of these, if you positively impact one, then the others negatively get impacted. For example, faster print rates, that can be done with more lasers, but that tends to negatively impact the cost of the equipment. And the same thing with labor. If you want to add automation and have less labor, well, that again will increase the equipment costs. The approach I do commonly see with the engineers in additive is having clever designs to help drive down the cost, whether this is lattices or printing in certain orientations. There are all kinds of things being done in the additive manufacturing world to try to get the cost down through clever designs. Now, I do want to talk briefly about my own company, my startup, Schooled LLC, and my PhD research, because what we are trying to do is approach this problem and address it to get additive more affordable. This new process, which I just kind of give a quick overview here, is called additive manufacturing evaporative casting, or AMEC. I'm not going to go into any of the technical details really, but if you want to talk to me about it after the talk, let me know. And how does this approach compare? So for raw materials in this case, we are actually, again, using the foundry ingot prices, $1.25, as I previously mentioned, for aluminum. And then we 3D print using basic FDM polymer filament. So that's pretty affordable for raw materials. Next, we use minimal infill, so it takes less time to print. And then we use much cheaper desktop printers, which have a pretty trivial amortized rate on a per pound basis, as well as if you need to speed things up, you can just get a wall of printers like some places do. And finally, from a post-processing standpoint, this process is based on lost foam casting. So it's about 0.3% accurate and needs much less machining. Now, the labor on this does need some work. Right now, this is a medium TRL process, and it's not quite yet ready for being in high production. But at some point, that would be possible to get this more automated. Right now, the labor that requires about the same amount of labor, whether we're making a 1 pound part or a 40 pound part. But looking at these assumptions, and kind of similar with the assumptions before, we actually can get a similar kind of costing for AMAC. And in this case, as I said, the raw materials, much less. The labor, and I did this analysis assuming a larger part so we could actually get the labor down. Otherwise, the labor would be much higher if we were looking at a 1 pound part. The equipment is very negligible, and post-processing, this has been scaled down to be similar to the above rates. So again, $3 per pound is not quite there yet, but it is definitely getting closer. And I think that this process, if we actually weren't looking at aluminum, if we were looking at something like A36 steel, actually you can take out a good bit of the cost from the ingot prices. So I want to show you the level of detail that's possible in AMAC. This is actually a zoomed in on a metal aluminum part, and you can actually see the 3D print striations they carry over from the polymer. And this is about a 1/2 inch wide section blown up here. But it does show you the kind of the level of 3D printing detail that's possible. So to wrap up my talk, I want to give you some predictions on where I see the additive market going. I actually think that the market is bigger than some of even the most optimistic forecasters think. I think that $2 per pound is really not crazy. But of course, sales price depends on value, not cost. And people will try to charge as much as they possibly can to sell parts. I mean, that makes sense, right? I think that the implications of metal AM dropping to a point where it's competitive on price with traditional manufacturing are huge. The amount of things that can be customized will go up a lot. But this will have a headwind in that the impact of those non-recurring engineering costs will become something that matters. And I've really totally ignored that in all of this analysis here. Finally, right now, a lot of cases people use AM for prototypes or very, very small volumes. But I think that the point at which justifying tooling is going to shift towards higher numbers. We think somewhere between 5,000 and 10,000 pieces. Above that, tooling would probably make sense. Below that, maybe it doesn't. Of course, this is going to depend on if you're using additive manufacturing to make part designs that aren't possible in other means. So in which case, you will not necessarily make tooling at all. So with that, I will thank you for your time, and I will open it up to questions.
Thank you for sharing your presentation, Sarah. It was fascinating watching you crunch numbers, and really, really cool to get an insight into what you're doing at your company over there. So I'll just throw it out to our audience. Did you agree or disagree with Sarah? What did you think of her forecasts? We can definitely discuss more on the networking site. So if you catch Sarah over there, then go ahead and feel free to argue with her, right?
Yeah. Part of this is just to make people think.
Absolutely. Absolutely. Thank you so much for sharing. We'll see you later on in the conference.
Yeah. All right. Well, thank you.